Good afternoon, everyone, and welcome to the second A-level chemistry session for the All Wales revision series. Okay, and today we're going to be looking at topics 8 and 9 of Unit 3. Okay, equilibria and acid-base equilibria. My name is Mr. Johnston, and Mr. Pickett is in the chat ready to answer your questions. First thing to mention is that, like last week's session, this session is being recorded and will be published online, so you can, make use of it at any time. So let's get straight into it. So our session objectives today are to do a bit of revision on AS equilibria. That includes Le Chatelier's principle and Kc calculations, the equilibrium constant for concentration calculations. Then we're going to look at A2 equilibria, including Kp, which involves pressure, the effective temperature on the equilibrium constant, and relating the equilibrium constant to the position of equilibrium. Then we're going to move on to some revision of AS acids and bases, okay, specifically the Lowry Bronsted theory of acids and bases and some key terms such as strong, weak, and conjugate. Make sure that we all know what those mean. And then finally, A2 acids bases, we're going to be looking at calculations, and there are quite a few calculations involving pH, Kw, Ka, and pKa, buffer solutions and associated calculations, and titration curves. And I forgot to put in there's some stuff in the titration curves about indicators as well. So let's start with Le Chatelier's principle by quoting it. If a system in equilibrium is subjected to a change, then the system will respond by trying to counteract the change imposed. Now, basically, this occurs because when you try and change a system that is in dynamic equilibrium, it will actually affect the rate of reaction of the forward and reverse reaction, but it will not affect them in the same way. So it will favor either the forward or the reverse reaction, depending on the change that you make. So, for example, okay, the Haber process that we all know and love. Okay, we have the key things here that we're going to be looking at. Okay, is that we have 4 moles of gas, okay, on the reactant side, and only 2 moles of gas on the product side. And also, this is delta H negative, so it is an exothermic reaction. Now, increasing the pressure of this reaction shifts the equilibriums towards the products, okay, because the increase in pressure increases the rate of the forward reaction more than it increases the rate of the reverse reaction. And that's because you've got more moles of gas in the reactants, so that increase in pressure is going to increase the number of collisions in the reactant particles more than the collision for the product particles, simply because you've got more moles of reactants than products. So that pressure increase is going to increase the forward reaction more. And then we'll have a look at temperature. So it's an exothermic reaction, and therefore it shifts an increase in temperature would shift equilibrium towards the reactants, or to the left if you prefer, because the rate of the reverse reaction increases more than the rate of the forward reaction. Now, it's worth noting at this point that increasing temperature always increases rate, so the rate of the forward reaction would go up, but the rate of the reverse reaction would go up more. Okay, and that's because the reverse reaction is endothermic, and the increase in kinetic energy would increase the rate much more than it would for the exothermic reaction, aka the forward reaction. Okay, so hopefully that makes sense. Kc calculations, so you touch on this in AS. Okay, now Kc is the expression, it's the letter we use to describe the equilibrium constant associated with an equilibrium in the solution phase. And it can be generally described if we have a system such as this. So I've just used small case letters to represent the stoichiometry, the numbers that go in front of the molecules, and capital letters to represent the reactants and the products. And it can be written like this: Kc is equal to concentration of the products raised to the power of their stoichiometry divided by the product of the concentration of the reactants, again raised to the power of their stoichiometry. So this is a nice general way of putting it. Okay, and it's worth pointing out at this point that the value of Kc is constant at a particular temperature. So changing concentrations of these will not change Kc. Temperature is the only thing that can change Kc. So here we have an example, okay, a reaction revolving around tetrachlorocobaltate, which you may recognize from topic 4 of unit 3, and we're going to react that with ammonia. This is not a reaction that you need to know, by the way, so if you're panicking thinking, oh, I don't know this one, this is not one that's involved, okay, but I've avoided a reaction that involves water. Okay, that's all I've done here. So if we have our Kc expression, it will look like this. Okay, so we take the concentration of the products and we raise them to their powers. So the this hexaamino cobalt 2 species is raised to the power 1, so there's nothing there. But because there's 4 chlorides, we raise the concentration of chloride to the power 4. And then we divide that by the sum of the concentrations raised to their powers. So the tetrachlorocobaltate is to the power 1 because there's only one of them. And then the ammonia is raised to the power 6 because there is 6 of them. And the square brackets represent the concentration of each species. The units of Kc depend on the equation. And to work that out, the best way to do it, okay, you can learn, you know, the values, the units of Kc in different situations, but the best thing to do is to cancel out the concentrations. So what I've done is units of Kc, I've combined all of the powers on the top and bottom lines. So I've combined the power 1 with the power 4 to get a total power of 5 on the top line, and then total power of 7 on the bottom line. Okay, and we're just raising the concentrations to those powers. Once you've done that, you'll see that there's 7 on the bottom, 5 on the top, 5 are cancelled out, and there's only 2 left on the bottom. So that gives us moles per dm cubed to the power of -2, which you can then simplify to moles to the -2 dm to the 6. Okay, so moving on. So in this example, in a given experiment, the initial concentrations of tetrachlorocobaltate and ammonia were 0.1 mole per dm cubed and 1.20 moles per dm cubed respectively. At equilibrium, the concentration of Cl- was found to be 0.6 moles per dm cubed. Calculate Kc. So this is a question where we have to work out the concentrations at equilibrium and then calculate Kc, because they've only given us one value of concentration at at equilibrium, and that is the chloride. Okay, so that's all they've given us. So this is a table of my own creation. Okay, basically, in order to calculate the concentration of every species at equilibrium, I will fill out this table. And I'm going to start with the initial concentrations. Now, I've been given the initial concentrations of the tetrachlorocobaltate and the ammonia, and I've just plugged those into the table under the title initial concentration. Now, the other two haven't been mentioned in the question, which means that they have no concentration to begin with. Okay, so they're just not there. Okay, and we've been told that at equilibrium, chloride has a concentration of 0.60. So that's all the information that we've been given. Everything else from this point, we have to work out for ourselves. Well, the first thing we can work out is we can actually use this concentration used / made row, okay, which basically will tell us, you know, how much of the concentration has been made on the product side or how much has been used up on the reactant side. And, you know, the reason I did this is because it is easy to get confused, okay, but we'll see how this goes. So if we've gone from 0 to 0.6 for the chloride, then it stands to reason that we've made 0.6 moles per dm cubed of chloride. And I put a plus there to show that we've made that we've added that to the system. Okay, now we use our stoichiometry, okay, our big numbers in front of the species, to work out the mole values for all of the others. And it makes sense to look at the other product first, because that's going to be a positive number again. So this is a 4-to-1 ratio. We simply need to then divide 0.60 by 4, which means that we have made 0.15 moles per dm cubed of this new species here. Okay, and so if we've added that to 0, then our equilibrium concentration is going to be that value. Okay, so it's 0.15. Once we've got that, whoops, okay, then we can start looking at all of the other ones, okay? But the key thing here, you may have noticed that my next value had a minus sign in front of it. That's because we're using up reactants. For the reactants, we're using them up, so we're subtracting that number. So looking at this, I think the best way to do this actually is to look at our new hexaamino cobalt 2 species, which has a 0.15 moles per dm cubed, and then that's a 1-to-6 ratio. So we take this value multiplied by 6 and we get 0.9, but it's minus 0.9 because we're using that up rather than making it. Okay, and that is key for this method. Okay, and while we're at it, we may as well do the tetrachlorocobaltate. Now, that's nice and easy. That is a 1-to-1 ratio. So, oh, nope, I've done it the other way around. So I've got 0.12 minus 0.9. I end up with an equilibrium concentration of 0.3. Okay, which so that's our final answer for the ammonia. Then it's a 1-to-1 ratio for the cobalt species. Okay, so 1-to-1, and so that's going to be minus 0.15. Same value, but we're taking that away because it's a reactant. It's being used up in the reaction, and so we just have 0.2 minus 0.15, and our equilibrium concentration is 0.05. Excellent. So we're now at the point where we have our equilibrium concentrations, which are the numbers at the bottom. Now we just plug those numbers into the Kc expression that we came up with earlier, which was this one. Okay, so we have this expression. We just put the numbers in, and there are the numbers. Okay, so there's our hexaamino cobalt 2, that just comes from there, so that goes straight into theirs, 0.15, and hopefully you can see where all the numbers have come from. We've just plugged the numbers in. Okay, and we end up with a value for Kc of 533.3 moles to the minus 2 dm to the 6. Okay, and remember where we worked out the units for this earlier, so we can just plug those units in. Okay, so hopefully this is jogging some memory on Kc expressions. Now we're looking at Kp, which is an equilibrium constant associated with an equilibrium in the gas phase. Now, of course, we can't use concentration for the gas phase because concentration is pretty much a solution property. So we can still describe this generally, and I've used the same layout as I did before, but rather than using concentrations, we're now going to be using partial pressures. Okay, so partial pressure of C raised to the power Y and partial pressure of D raised to the power Z. So it's again products over reactants raised to their powers. Okay, so it's the same situation, but using partial pressures instead of concentrations. And just like Kc, we've got Kp is constant at a particular temperature. Okay, temperature is the only thing that can change Kp. So let's have a look at an example for that. Okay, so we've got methane reacting with chlorine to form tetrachloromethane and hydrogen. Okay, all in the gas phase. So this is going to be a Kp expression, and we can write out the expression like so. Okay, partial pressure of products over partial pressure of reactants, all raised to their powers. So So we've got tetrachloromethane here. That's raised to the power 1 because there's only one of them. Hydrogen is raised to the power 2, partial pressure of hydrogen there. And again, methane raised to the power 1, partial pressure of chlorine raised to the power of 2. Okay, now again, the units depend on the equation. Okay, and again, we just cancel out the units of pressure. And in this example, I'm using atmospheres. You could also use pascals, kilopascals, work with what you're given, okay? But I've used atmospheres here, okay? But it doesn't actually matter which one we use this time because we've got atmospheres to the power 3 over atmospheres to the power 3. Those cancel out completely and they equal 1. So we end up with no units for this particular expression. Okay, if this was pascals, it would just be pascals to the power 3 over pascals to the 3. So it wouldn't make a difference. You'd still end up with no units. Now, some of you may be thinking, well, what is a partial pressure? Because, I brought this up in the in an earlier part of this. Partial pressure is the pressure exerted by one of the gases in a mixture of gases. Okay, so it could be, in our example, the partial pressure of methane is the pressure that's just exerted by the methane. Now, to work these out, you need to find the mole fraction of the gas in the system. Okay, which mole fraction of gas A, oops, I'm missing a space there, but never mind. Okay, basically, if you had a system with gas A in it and a load of other gases, the mole fraction of A is just the moles of A divided by the total moles of gas in the system. Okay, so and you would work out moles using one of the methods that you used in that you learnt about in AS. Okay, and they'd give you information to work that out, and then you just calculate partial pressure by taking the mole fraction of A, which you've worked out earlier using this expression, and then multiplying that by the total pressure. So let's say the mole fraction of gas A turned out to be 0.25 and the total pressure was 4. Then you'd end up with 0.25 times 4. You'd end up with partial pressure of A being 1 atmosphere, let's say. Now you may be given a percentage of a gas instead. Okay, this is also a common one. Okay, so they might not make you do mole fractions. They might just give you a percentage. Say that it is, 60%, hydrogen, for example. In which case, the partial pressure of A would be the percentage of A that they've given you divided by 100, and then multiply that by the total pressure. Okay, so this is an alternative, and to be honest, this one is becoming more and more common. So let's have a look at an example, and we'll use the chemical reaction that we had before. So in a given experiment, the initial pressure of the reaction was found to be 505,000 pascals. The initial reaction mixture was 40% methane and 60% chlorine. At equilibrium, the partial pressure of tetrachloromethane was found to be 75,750 pascals. So that should say afterwards, calculate Kp. So again, we need to calculate the partial pressure of every species in the equilibrium. And again, we're going to use a table for that. Okay, this is again a method that I use and I think is really useful. So we fill in the information that we know. Now, what we know is that the total pressure is 505,000 pascals, and that the reaction mixture is 40% methane and 60% chlorine. So what we do is we work out 40% of 505,000 to get our partial pressure of methane. So we work out 40% of that, and it turns out to be 202,000. Okay, so that's fine. Then we work out 60%, or you can just subtract that value from the total to get our chlorine value, which is 303,000. And because the products haven't been mentioned, we just put that at 0. They haven't been used yet. Okay. And then we're told that tetrachloromethane has a partial pressure of 75,750. And so we can bung that in there. So again, we can work through this. This is all we know, but we know, for example, that we must have added 75,750 pascals. Okay, and that should say say pressure used or made, not conc. I apologize for that. So again, we use the stoichiometry to work out our values. So looking at the products again, 1:2 ratio. So we just multiply this value by 2 to get the value of hydrogen, and we end up with 151,500. Okay, and we're adding that because it is a product, it is being made. So we add that to 0 and we get 151,500 in total. Now we do the same thing where we have to work out how much of each one is used. So we'll start with chlorine simply because it's closer. It's a 1:2 ratio. So it's going to be exactly the same value as for hydrogen, but it's going to be minus because we're using it up. So we then subtract 151,500 from 303,000, and we get a total of 151,500. Okay, and that is the value at equilibrium for chlorine. Same thing for methane. We've got a 1:1 reaction, so we've got the same number as for tetrachloromethane, but it's minus because it's being used up. And then we just subtract 75,750 from 202,000. We end up with, let me get this right, 126,250 at equilibrium. So now that we've got that, we've got those numbers, we plug in the numbers again, and we've got our expression from earlier, which we worked out earlier. So we just put the numbers in. That's what we end up with, and then we work that out and we end up with a value of 0.6. And notice how there are no units there because we worked out earlier that there are no units for this expression. So it's a very similar procedure whether you're working with Kc or Kp. Quickly, the relationship between equilibrium constant and temperature. Okay, the effect can be deduced using Le Chatelier's principle. For equilibrium was an exothermic forward reaction. Temperature increases, the endothermic reverse reaction is favored. There will be a decrease in the products formed, and so the equilibrium constant will go down. Okay, so increasing temperature of an exothermic reaction will decrease Kc or Kp. Now, if the equilibrium has an endothermic forward reaction, then we increase the temperature, we increase the rate of the forward reaction, and so we increase the amount of products formed, and so we end up with an increasing temperature, increasing Kc or Kp. Right, okay, so that's the first topic done. Let's go on to the second. Bronsted-Lowry acids and bases. Bronsted acid is a proton donor, so it gives H+ to something else, which is the base, which is the proton acceptor, so that takes the H+. An alkali is a water-soluble base. That's something that we need to know. Then we talk about conjugates. A conjugate base is the species formed when an acid donates a proton, so it's essentially what's left once the proton has been removed from the acid. Conjugate acid is the species that formed when a base accepts a proton. And if we have a look at an example here, we've got nitric acid reacting with sodium hydroxide, okay, and we're forming sodium ions, nitrate ions, and water molecules. Now, the acid is the species that's giving up the proton. So nitric acid, HNO3, is the acid because it starts with a hydrogen, but it has lost it on the product side. The base is the species that accepts the proton. and so that is the sodium hydroxide, because the hydroxide ion has accepted a proton to become water. The conjugate base is what forms when the acid donates a proton, so that is the nitrate group. And then finally, the conjugate acid is the species formed when a base accepts a proton. Well, that is the water, because the OH minus has accepted a proton and become water. Okay, so moving on. Strong acid fully dissociates into H plus ions and the conjugate base when dissolved in water. An example of that is, for example, sulfuric acid, which fully splits up from H2SO4 into 2H plus and SO4 2 minus. Okay, and it does that completely. Okay, this is not an equilibrium, it is a full-on reaction. A weak acid partially dissociates into H plus ions and the conjugate base when dissolved in water. This establishes an equilibrium. So this is the one with the equilibrium sign in. So classic weak acid, ethanoic acid, establishes an equilibrium with the fully formed acid molecule and the H plus ions and the conjugate base, the ethanoate ion in this case. Okay. The weak acid equilibrium is often represented generally by the following. So I'm going to be using this, notation. Okay, HA splits up into A minus and H plus. Now, the acid dissociation constant, which is known as Ka, is the equilibrium constant for the dissociation of a weak acid. So this is now getting into new territory. So there's our equilibrium again. Okay, and using the same formula that we used for Kc and Kp, this is our expression for Ka. So concentrations of the products raise their power. In this case, all the powers are 1, so that's nice and simple. Divided by concentrations of the reactants, which in this case is Ha. Again, raise the power 1, so no complicated powers there, which is nice. Now, because this is the same formula for all weak acids, okay, because all weak acids you're going to be dealing with are monoprotic, they only give off 1 proton, then the units of Ka are always moles per dm cubed. Okay, and Ka can be used to calculate a value called pKa, which is very, very similar to pH, which I will, refresh you guys on later when we start going through some pH calculations. But to work out pKa, it's simply negative log of Ka. Okay, and the reason we do that is basically to make the numbers a bit simpler, a bit easier to handle, and we end up with the lower the value of the pKa, the stronger the acid. Which means that if we work out the pKa of 2 weak acids, we can work out which one is a bit stronger, dissociates a bit more in water. Right, okay, so we also need to know about the ionic product of water. Water molecules partly dissociate into H plus ions and OH minus ions. Okay, not very much at all, but we use the same formula as we've done for Kc and Kp, and we end up with Ka. This is a special case, okay, OH minus H plus over H2O. But because only a tiny fraction of the water molecules dissociate, the concentration of H2O is considered to be constant. We combine this constant with the value of Ka from this equation, and we end up with a new expression to calculate something called the ionic product of water, which is a nice simplified Kw equals concentration of OH minus multiplied by concentration of H plus. Now, the value of Kw is constant at a constant temperature, and you need to know that at room temperature, that's 298 K or 25 degrees Celsius, the value is 1 times 10 to the minus 14. Okay, that's something you need to know. In pure water, these values are equal. Okay, so OH minus, H plus, they're equal, which you can see there. So Kw ends up equal to concentration of H plus squared, which at room temperature is 10 to the minus 14. So pure water has a hydrogen ion concentration of 10 to the minus 7 moles per dm cubed. And if you do a pH calculation on that, it comes out at pH 7. So, which matches perfectly with what pure water should be. Right, when we add an acid or a base to the water, the value of Kw remains constant. And this is really, really important. So even if you add a strong acid to water, Kw is still 1 times 10 to the minus 14, provided that you haven't changed the temperature. So let's calculate some pHs. Now, as you may remember, pH is equal to negative log to the base 10 of concentration of hydrogen ions. And the reverse of that function is hydrogen ion concentration is equal to 10 to the power of minus pH. Okay, you need to know both of those. Now, for monoprotic strong acids, okay, such as HCl and HNO3, the value of H plus is the same as the concentration of the acid itself. So that's nice and easy. Obviously, if you had sulfuric acid, you'd have to double the concentration of the acid to get the concentration of H plus. So if we look at a pH of a solution of HNO3, of nitric acid, 0.2 moles per dm cubed, we put in 0.2 into the negative log value, and we end up with a value of 0.70. That's the 2 significant figures. Okay, so that's a very, very strong acid. Now, for strong bases, it is possible to calculate the pH of the solution when you know the concentration of OH minus ions. That's the easy bit to know. Okay, it's very difficult to know what the concentration of H plus is when you've added, say, sodium hydroxide, but you can work out the concentration of OH minus really easily. So here's my concentration of sodium hydroxide. Okay, and they will be this. So the concentration of OH minus will be the same as this. Again, sodium hydroxide only releases 1 OH minus. Okay, we rearranged the Kw equation. Okay, it's a nice simple rearrangement from Kw equals OH minus times H plus to H plus equals Kw over OH minus. Once we've got the value of H plus, then we can work out pH nice and easily. Okay. Now I've mentioned here that again, Kw is 1 times 10 to the minus 14. If the temperature is different, you'll be provided with a value of Kw for that particular temperature, but you are expected to remember this one. Okay, so we work that out and we end up with a concentration of H plus for this solution as 2 times 10 to the minus 14 moles per dm cubed. Once we've got that, we put that into the pH equation, and there we go. Okay, so we end up with a pH of 14.70. So I'm going with very strong acids and alkalis today. Right, so moving on. Calculating pH for weak acids is a little bit more tricky, okay? But we have to use Ka values in order to do that, okay? So we use our Ka expression here. Now, since each molecule of HA that dissociates forms one H plus and one A minus, we say that H plus is equal to A minus. Therefore, we can rearrange this expression into Ka equals H plus squared over HA. Once we've got that, okay, we can basically say that the concentration of HA is the same as the initial concentration because it dissociates so little that it practically is the same concentration. So we end up with this expression. H plus is equal to the square root of Ka, should have subscripted that, times by HA. Okay. And then once we've used this, once we've got that formula, we can make use of it. So let's calculate the pH of a 3 mole per dm cubed solution of phenol. Okay, and the Ka of phenol is 1.3 times 10 to the minus 10. So we just plug in 1.3 times 10 to the minus 10, multiply it by 3, and then square root it. And we end up with a H plus concentration of 1.96 times 10 to the minus 5, and that should be moles per dm cubed. The pH, we then plug that in to the minus log H plus expression, we end up with a pH of 4.70, okay, to 3 significant figures. Okay, so that's how to calculate the pH of a weak acid. Now, if we've got the pH of a weak acid and we've got the concentration, then we can calculate Ka, and this is probably an easier thing to do. Okay, so we measure the pH using a pH probe or, a universal indicator or something along those lines. Okay, we get a pH value and we can calculate the value of Ka. We just have to use the adjusted version of the Ka formula, which we used earlier. So if we've got Ka for a weak acid with a concentration of 3.5 moles per dm cubed and a pH of 6.30, then we can work out concentration of H plus using the 10 to the power minus pH formula. So we plug the pH in there and we end up with 5.01 times 10 to the minus 7. That should be moles per dm cubed. Ka is equal to H plus squared over HA. So then we just plug those numbers in because we've got 5.01 times 10 to the minus 7 for H plus, and HA is the same as what we were given in the question, 3.5. So there we go, we plug those numbers in, and Ka comes out for this particular acid at 7.18 times 10 to the minus 14 moles per dm cubed. Okay, so calculating Ka from pH, is pretty simple. Now, I will talk a little bit about buffers. I know I'm running short on time, so I'll just quickly go through, what a buffer is. I think this is really important. Okay, so acidic buffer solutions, basically, buffer solutions are solutions which maintain a near constant pH when you add small amounts of acid or alkali to them. Okay, and in this case, we're going to make an acidic buffer solution. It's made of a weak acid, such as ethanoic acid, and then a salt that is made from that weak acid after it's been reacted with a strong base. Okay, so I've got here sodium ethanoate, which is basically the reaction between ethanoic acid and sodium hydroxide. Okay, and this acts as a source of A minus. Okay, the conjugate base of that weak acid. Okay, now the buffer solution maintains a high concentration of the conjugate base as the salt dissociates completely. So that sodium ethanoate is going to split up entirely into ethanoate ions and Na plus ions. The weak acid partially dissociates, as weak acids do, and sets up an equilibrium of the ethanoate and H plus against the weak acid. And because there's already a high concentration of ethanoate ions, the equilibrium is forced to the left and the acid is almost all in the undissociated form. Now, I just want to talk quickly about what acidic buffers do when you add acid to them, okay? And then we'll finish there. So when an acid is added to a buffer solution, the concentration of H plus increases, the equilibrium will shift to the left as the conjugate base reacts with the H plus ions, removing them from solution. So you add H plus, the H plus reacts with the ethanoate, and it goes and forms ethanoic acid, okay, which does not contribute to the acidity because the H is attached to it. Okay, so the ethanoate reacts with the H plus if you add H plus. When you add an alkali, the OH minus reacts with the H plus ions in solution and it removes them. Okay, and forms water in the classic, neutralization equation. Then this shifts the equilibrium to the right, producing more H plus ions to remove the ones that were removed, to replace the ones that were removed. Sorry. So your ethanoic acid will then dissociate a bit more and release more H plus. Now, that's our time, I'm afraid. So there is a lot more to this, but I am going to quickly go through this. This PowerPoint will be available online, so hopefully this will be helpful to everyone. Okay, I'm just quickly going to go through to the end and say my goodbyes. Okay, I've got useful links again. Again, it's the experiments on film. Experiments 17 and 18 will be really useful for this topic. Okay, the blended learning revision guides, on WJC. Really, really useful. Okay. Thank you very much for listening. Thank you for your time. Next week, it will be Mr. Pickett's turn, and he's going to be doing some organic chemistry with you guys. We're going to be doing some Unit 4. So do remember, this PowerPoint will be published online for you guys to use. Okay, so don't worry that we didn't get around to doing a lot of it. Okay, you will have access to it. Thank you very much for your time. I hope you have a fantastic day. Take care. Bye-bye.